Right, today's class is about minimal and the maximum values of the function. Right. Before we talk about minimal value or maximum values, I'm going to go over the tangent planes of the graph of a function. Okay. We know that if the surface is determined by an equation, okay, and this is a surface, and this can be constant k. It's level. It's a level surface. Okay, it's a level surface. In this case, and the gradient of the function will be the normal vector. Okay, the gradient of function at that particular point is a normal vector. Okay, so you know how to define this, right? Gradient of this. So this is a normal vector. Okay, it's a normal vector, so it's perpendicular to the tangent plane. Now, how to find the equation for the tangent plane? It's very simple. Take an arbitrary point on the tangent plane. Okay, x, y, z. Okay, and draw the line, and you get a tangent. You get a tangent vector, which lies in the tangent plane. Then there must be perpendicular. So the tangent vector is x minus x naught, y minus y naught, z minus z naught. Okay, that's the difference. And the dot product was a gradient. Okay, should be equal to 0. Okay, that's the equation for the tangent plane. Tangent plane. Okay. The special case, okay, consider the special case is that f be defined on a domain V in R2, okay? Then the graph can be viewed as level surface. So the graph of f, okay, which is the graph of the equation, is the graph of the equation z equals f of x, okay? And that is the equation, okay? And it is also, so this is a graph, right? And you can also change it to z minus, it doesn't matter which one is first, z minus f of x equals 0. Okay, right, it's the same. So this is my capital X, Y, Z, f of x, y, z, okay? So what is the gradient of this function? Okay, let z naught equals f of naught, y naught, okay? So at this particular point. So this is a graph. And this is a graph. This graph can be viewed as a level curve, a level surface of some function in 3 variables, which is z minus f of x. Okay. So at this particular point, okay. And so the gradient of f is going to be the partial derivative of capital F with respect to x, which is fx, negative y, and then 1. Okay, you differentiate each, differentiate this one with respect to x, y, z. Now this is actually is going to be a partial derivative of capital F, right? By definition. Okay, so after you calculate it, you get the above components. Okay, so the tangent plane at the point, okay, is given by the following equation. x minus x naught, y minus 1, z minus z naught. And here the dot product was this vector, right? Okay. And when you multiply this out, what do you get? You will get negative, okay, minus, and plus z minus z0, okay, equal. So this is the equation of the tangent plane, okay? Now you can also move this term to the left side, to the right-hand side. So you can simply write okay, that's the equation. Okay, so the tangent plane, we have the most general formula, then you get a very specific formula for the graph of a function. A graph of function can be viewed as the level surface of a function of 3 variables. I have the function of this function will be just difference of z minus f of x. Okay. Yeah. So that's a point. So when you look at here's a question: when this tangent plane is horizontal, okay? If the tangent plane is horizontal, think about that. Tangent plane is horizontal, okay? It's in that position, right? Tangent plane is in horizontal if only if the gradient of the normal vector is going to be vertical, right? Vertical means the first component, second component, 0, okay? So here's a key point, okay? So you consider the most general case, okay? At that particular point, the tangent plane is horizontal, okay? At the point, if and only if, okay, the gradient of f, this is normal vector, is going to be the first component 0, second component 0, the third component we don't care. So you just put a star there, doesn't matter. Okay, it must be in this form, right? Now, if capital Fxyz is going to be z minus f of xy, okay? So that means the level surface is going to be the graph of this function, okay? Then the above formula says that the tangent plane, okay, is horizontal, okay? At that point, if and only if the first two components are 0. The gradient of this capital F, the first component is negative, the partial derivative, so that's going to be 0. That is also going to be 0, the second component, okay? So, yeah, you can calculate the gradient, right? If this one, the gradient will be, the gradient F will be, the gradient F will be negative partial, right? Negative partial. Partial derivative F with respect to y and z1, okay? So that's why the first two components must be 0. So that's it. Now let's take a look at, the function, okay? We're going to find out when the function has a maximum value, okay? Here's the definition, okay? Okay, function f is defined on the domain, okay? This is a function, this is the domain, D, okay? And here's an arbitrary point, okay? So a function f, okay? So here's the definition. We said that a function has a local maximum value if the following is true, okay? So f of x naught y naught is a local maximum value of f, okay, if the value of function for x close to that point is always less than or equal to the value, okay, for x, y close to, yeah, for x, y, let's say nearby that particular point. So you can have a small neighborhood of that point. The value of function is always smaller than less than or equal to the value of the function at that particular point. Okay. Now, local maximum does not mean it's global maximum. Okay. I'm going to draw the graph of the picture show to you. Okay. So you can see that this is a picture. Okay. And this is my domain. D. Okay. This is a graph. Okay, like a mountain. Okay. And it's defined on that. And this is a point, right? And then this is a point. Okay. So this is local highest point. Okay. So here, okay. So this is a graph, and z equals f of x, y. Okay. And the function has a local maximum value. Okay. The local maximum value is a z naught, right? Which is given by the value of the function. All right. So now the question is, how do we find them? How to find them? Right? But at this highest point, if we put a tangent plane there, okay, the tangent plane must be horizontal. So a simple observation shows you that, the tangent plane must be horizontal if the function is differentiable at that point. Okay? If the function is not differentiable, then you cannot talk about single tangent plane. Okay? So the simple observation leads to the following theorem. Okay. Okay. If f has a local maximal or minimal value, okay, at this particular point, and we also have to assume the function differentiable, and f is differentiable at that particular point. Okay, then this is a necessary condition. Then the tangent plane must be horizontal. The tangent plane at that particular point, right, is horizontal. And this is equivalent to saying that the partial derivative is going to be 0. Okay, this is very similar to the theorem in for function in one variable. A function is differential. The function has a local maximum value or minimum value at some point, and the tangent line must be horizontal, so the derivative must be 0. Of course, it's possible that point is not differentiable, so this is another case. So if you want to find the local maximum value of function, right, this theorem is very useful. All you have to do is find the points where the function is not differentiable, and find the points where the function is differentiable, but the derivative should be 0. Those are called the critical points. Okay, those are called the critical points. Okay, so let's take a look at example. A good example here is f of xy is going to be x squared plus 3y squared. Okay. So this is so if you draw the graph, okay, how does the graph look like? The graph looks like that. If you're able to draw the graph, you probably already know the result. So the graph looks like that. Okay. Okay, this is an axis, this is y-axis, this is a z-axis. It's a paraboloid. Okay, each cross section it is an ellipse. Okay, not a great circle. Okay, ellipse. Okay, it's ellipse. Okay. So this function has a local minimum value at its origin, and let's prove it. Okay, this function, if we can draw the graph, you can see already. This has local minimum value. Okay, so assume that now I don't need to assume that. Yeah, I just find the partial derivative first, and I'm going to find out those points at which the partial derivative is 0. Okay, that'll be 2x. Okay, f sub y x y. That's going to be 6y. Now, if I set them to 0, the only solution I got is going to be xy is going to be 0, 0. Okay, this is the only candidate. Okay, this is the only candidate. So if the function has a local minimum value and it only occurs at this point, okay, if the function has a local minimum value, okay, then it must, you don't need to look at other place. It must look at this particular point, okay? That just only help you to find local minimum value or local maximum value. But you can also, without using calculus, you also can tell that, okay? Without using calculus, without derivative, you can already see the local minimum value. Actually, it's an absolute minimum value. So for any x and y, the function of the value of the function is x squared plus 2 plus 3y squared. And clearly this is always greater than or equal to 0 squared plus 3, just greater than or equal to 0. Okay, right? And this is as a value of the function at 0 and 0. So, and if it's not going to be 0, and this is a strictly greater than 0 actually, okay? If x and y, one of them is not going to be 0, that's very positive. So clearly f has a minimum value, actually it's absolute minimum value. Yeah, let's just say at local minimum value, okay? What is the minimum value? It's going to be 0, okay? This minimum value it occurs at origin. But it's not easy to it's not easy to check whether kind of the function has a local minimum value or maximum value at a particular point. Okay, even you find out as the derivatives are 0. Okay, let me give a definition called a critical point. Well, in the book, probably does not mention that. It's usually called a critical point. Okay, a point is called a critical point if either the function differentiable at that point or the function, the partial derivatives are, if a differentiable, then must be 0. Okay, so a point is called a critical point if, okay, if f is not differentiable at this point, or f is differentiable, and then with 0 derivatives. Okay, So those are called different. This is called the critical point. Then the function, the local maximum value or local minimum value only occur at the critical points. Okay, right? Easy, because when you go back to the theorem, says that if the function is differentiable, then at that point, then the derivative must be zero. Okay, so above theorem says that the function, it occurs different. You know, this is this is how do we, you either it's differentiable, the function is differentiable, or not differentiable. If it's not differentiable, it's critical. It's also easy to find out. Okay, so the most challenging work is to determine whether the critical point has a local maximum value. Yeah. Okay. So let's take a look at the problem. This is here's the problem here. F of x, y is going to be, I just changed this problem to this one. Okay. Okay. So now, I can even put 2x here, doesn't matter. Okay. So let's take a look at this. Let's find the critical point first. This function always is differentiable. So if partial derivative is 0, then you get a critical point. Okay, it's differentiable everywhere. 2x plus 2 is negative 6y. Okay, if we set this to be 0, what do you get? X get a negative 1, and you get y equals 0. Okay, so you only have one critical point, which is negative 1, 0. Okay. But the question is whether the function has a local maximum value or local minimum value. Right? This is our the challenging work we have to figure out. Right? Without further using calculus, okay, how can I do that? Right. I can work on this function directly. Okay, so I modify this function. First of all, I modify this function, which is going to be x squared plus 2x plus 1, and then I modify this a little bit. So it's actually is x plus 1 squared minus 3y squared minus 1. So negative 1 here is the value of this function. Okay, this is going to be negative 1. I cannot tell the function is always greater than or equal to the value. Okay, it's a question. Yeah. So do you think this is possible for x and y close to this point? No. Okay. And you can see that directly. Okay, sometimes yes, sometimes it's smaller. For example, if I let for all x, y close to negative 1, right? So how about like this? If I let the x to be 0, and then I got negative 3y squared minus 1, okay? Which is less than, okay? Which is less than negative 1. Negative 1 is going to be f and negative 1, 0. Okay. No, I put a negative 1 here. Yeah, sorry, no. Okay. So for if you draw the picture here, negative 1, and this is one. For points along this line getting close to that point, the value of the function is always smaller than the value of the function at that particular point, negative 1, 0. However, if you consider the points along the x-axis, then you get x plus 1 squared minus 1, which is going to be greater than, okay, negative 1. So some, no matter how close to the point, the value of the function could be either greater than 1, negative 1, or less than negative 1. So it's not always on the one side. So that implies, this implies f -1, 0, which is -1, is not a local maximal or minimal value. Okay, we get that directly because the function is easy to figure out, you know. But in general, it is difficult to figure out this. Okay, if the function is more complicated. Okay, so what I'm going to do is, I assume, okay, what I'm trying to do is we assume that f is differentiable many times at this point, okay? And I also know that this is already a critical point, right? So I want to see how can I check whether the function has a local maximum value, local minimum value, right? And we use a so-called second derivative test. This from we have the theorem for the second derivative test, okay, from S165. So we're going to use that to get a second derivative test for this function. Okay. So I consider ht. Okay, this is going to be an arbitrary value, right? Here's a tu and y0 plus tv. Okay. So how does this function look like? Okay. So first of all, let's find the derivative. Okay. So when t equals 0, yeah, first of all, when t equals 0, this is just a value function, and no problem. Then I differentiate once, partial derivative. And that's u, okay, plus fy, that's a v, okay, that's the first order. I also want to find the second derivative. Okay, it's more complicated. I should get total 4 terms. What I get here is going to be f, when I differentiate the top one, yeah, I get u squared, okay? Then I differentiate with respect to y, and then I get uv, okay? Then I differentiate with the second term with respect to x, then I get vu. Then I differentiate second term with respect to y. All right, so those are the second derivative. Then I also look at what is this, okay? So when I plug 0 for t into the above formula, I get okay, and this is going to be 0. We already assumed that. So 0, t equals 0 is a critical point for the function h. Okay, then I look at the second derivative. The second derivative, you only have 3 terms because x, y, yx, sub x, you know, partial derivative that can be put together. Yeah, u and the v, and then fyy v squared. So this is the second derivative. But I want to express it using matrix form. Okay, using matrix form, I got fxx. Okay, let me use the matrix. So if you took mass 171, and this, you're familiar with this notation. So this is a UV matrix, and here xy, and I can change the order here, yx. It's actually the same. Fyy and that is a u and a v. Okay, so this is a all right. So now think about, right? We consider the function when the second derivative test in from math 165. It says that if h prime is 0, 0, and h prime double prime is positive, right? Yeah, we are now we don't just two cases here. Yeah. So if the second derivative is positive, then this is going to be is a local minimal value, right? Minimal value of the h, not the f. Okay? If h this is negative, then this is a local maximum value. That's what we learned from calculus course, the first calculus course. Okay. All right, so this is second derivative. Now, how do we apply this result to the above problem? I think here the second derivative is a product of this, vector matrices. Okay, so you can as long as this matrix is positive definite, okay, then f double prime is going to be 0. Is going to be positive. So you can translate this result to the second derivative test for the function was in two variables. Okay, for the function fxy. Okay, so assumption. Okay, assumption is the derivative, partial derivative is equal to 0, right? So then for the function, I just simply write was, okay, so this is a critical point. Then first, h double prime is going to be positive, right? H double prime positive means this matrix. Okay, so if for any direction, okay, this matrix is positive, and I'm not going to fill the details here. Okay, then this one is a local minimum value. Okay. And similarly, if for any uv not equal to 0, okay, this product is negative, then this is going to be the local maximum value. Okay, and why this is true? Okay, let me draw the picture again. Explain to you. Okay, so this is a now I just need to draw a 2D picture. Okay, so here's the domain. Okay, D, and this is a point x naught, y naught, right? So an arbitrary direction in uv. So the function is restricted to, h over t is a restriction of function to this line. So the function has a local maximum value. Right? The above condition implies implies this function h of t is greater than or equal to h of 0, right? That means along this line, the function has a local minimum value, okay? Local minimum value at this point. But then all the lines, you know, the function always along all the lines passing through this point, the function has a local minimum value. So the first condition, let's look at the first condition. The first condition is just the second derivative of h prime, right? So h double prime is going to be positive, okay? Implies ht is greater than h0 for t not equal to 0, close to 0, okay? Right? So that means the value of the function along this line is greater than or equal to the value of the function at this particular point, okay? But you have to make sure in all the direction it has such property. Okay? Then you say the function has a local minimum value at this point. Okay, if it's just only one direction, it's not useful. Okay, if in one direction, you cannot say, yeah, like the second example I discussed. In some direction, the function has a local minimum value. In some direction, along some line, the function has a local maximum value. Okay, just like the saddle point. All right, so this is the question is how can I check a matrix is positive definite? Okay, this is a linear algebra problem. Okay, a matrix A and B and B and C. Okay, this one is a positive definite. How to check whether it's positive definite? Okay, so I'm going to give a matrix. I'm going to take as a determinant, which is AC minus B squared. Okay, a matrix is a positive definite. That's the first condition, right? UV, A, B, B, C, UV, it's always positive for any UV if and only if you can check that if and only if and these are positive, A is positive, okay? Simple, right? And then UV, A, B, B, C, UV is always negative. For any UV, that's linear algebra, if and only if determinant is still positive, but the A should be negative. Okay. And if what happens if D is negative or D is 0, then inconclusive, I cannot say anything. So D must be always positive. Then you can talk about local maximum value, local minimum value. So for an arbitrary symmetric matrix, this is how do we check whether this is always positive or always negative. Okay, just look at the coefficients. Okay, look at the determinant, then you look at the coefficient. Okay. All right, so take a look at take a look at the following example. Right. So let's look at the following example. Okay, you have an x and y, x to the fourth power y to the fourth minus 4x times y. Right. And we want to find out, find the local maximum minimum value. Find the local maximum minimum value, okay, if any. So this function, it's hard to draw the graph right now because x to the fourth power plus y to the fourth minus 4xy. Okay. All right. So first of all, let's find the critical point. Okay. It's a 4x cubed minus 4y, right? Then partial derivative is 4y cubed minus 4x. I'm going to set this to be 0. Now, how do you solve this? This I have to be careful, right? So you get two equations. Right. I use a substitution. Okay, it's not a linear equation, right? Use a substitution. I get, yeah, the x cubed, right? X is going to be y cubed. So y cubed, okay, cube minus y equals 0, right? Yeah, replace x by y cubed. So you get y to the ninth minus y equals 0. You have y to the eighth minus y equals 0, right? So what do you get? You get two solutions, y equals 0 or y equals plus minus 1. Wow. Because y to the even power equals 1, then y must be plus minus 1. Okay? So when the y is 0, x is going to be 0. Okay? When the y equals plus minus 1, x is also going to be plus minus 1. Yeah, because x is y cubed. So when y is negative 1, x is negative. When y is positive 1, x is positive. Okay, so you got 3 points. Critical points are 0, 0, 1, and 1, and negative 1, negative 1. So we have to check each of them. Okay. We have to check each of them. Okay. So using second derivative test. So I'm going to find the second derivative of the function. Fxx is going to be 12x squared, okay? Fxy, I'm going to differentiate to negative 4, okay? Fyy, it is going to be 12y squared. So let's evaluate each of them, right? The matrix. So I'm going to let, yeah, let's just look at the matrix. Okay, at the point 0, 0, this matrix okay, is going to be when x equals 0, that's a 0, and it's negative 4, negative 4, 0, okay? And this, unfortunately, in this case, d is 0. I cannot say anything about that. Okay? The match is not definite. Okay. Then I have to pay attention. We come back to this, whether this function, this is it's a local maximum value or local minimum value at this point. Okay. At this point, the value of the function, right? The value of the function is going to be 0, 0. Okay. So I'm not sure 0 is a local maximum value, local minimum value. I cannot use second derivative test is 0, just because the determinant is 0. At the point when 1. Okay, I got 12, negative 4, negative 4, and 12. So let's look at the determinant. Determinant is going to be the matrix. It's 12 square minus negative 4 square. This is positive, okay? This is 144 minus 16. Anyway, it's positive. Okay. And the first term is also positive. 12 is a positive. Okay. The first one, xx, is also positive. So that implies F1 and 1. Yeah, F1 and 1 is the value of the, right? It's going to be, let's calculate the value. This is a 1 to the fourth power, 1 to the fourth, so minus 4 times 1 times 1. So equals -2. This is going to be a local minimum value, okay? Because this is a positive definite, okay? Yeah, this is, we simply write like that. This is a positive definite since you have these two conditions satisfied. All right, so now the function has a local maximum value, okay? So if you draw the graph, I cannot draw the graph, okay? The graph passing through the origin. At the point when here, the graph is as local as the local minimum value, okay? This is the one. And at another point, other side, somewhere here, let me draw the picture, okay? So this is a 1 and a 1. Yeah, it's hard to draw it. I only can see a local small piece here. Okay. So at the point -1, right? The function, the value of the function is going to be -1 to the fourth power plus -1 to the fourth power minus 4 times -1 times -1. So you still get the same value, it's -2. Let's look at the matrix. Okay, the matrix where's the value? The matrix here is 12 x squared, so it's 12 -4 -4 12 y squared. So it's still positive, definite. Okay, so that means I don't repeat the computation. So F -1, which is -2, is a local minimum value. So the graph looks like that. Okay, and how do we connect them? We don't know. It's harder to draw it. But the graph passing through the origin. I don't think it's possible it looks like that, maybe. Yeah. I'm not sure the graph, it has a local maximum value or not. Okay. So let's, if we, we have to do something else to figure it out. Okay. So let's take a look at the function again. X to the fourth, y to the fourth minus 4x times y. Okay, I know the value is going to be 0. Are we able to figure out whether the function has maximum value or has minimum value? Okay. Okay, let's take a look at along the x-axis. Okay, along the x-axis, y is going to be 0, right? So it's going to be x to the fourth. This is positive, which is the graph is around above that point. Along the y-axis is the same. It's going to be positive, right? Of course, here's x is not 0, here's y is not 0, otherwise. So this is can I find another line so that it's going to be negative? Okay, that's possible. Okay, so this is a picture, two-dimension picture. Okay, along this x-axis, along the y-axis, the value of the function is positive. Let's say positive, right? So how about this line? Okay, let's say x equals t, y equals t. So f, t, and t. and then t to the fourth power, t to the fourth minus 4 times t. So I get t to the fourth power minus 4t squared. Okay, I can take a t squared out. So I have a t squared minus 1. Aha, now I can make it a negative. Why? When t is small, this is a negative for t is close to. Okay, so that means here negative. So somewhere positive, some negative. So this the value of the function is not a local maximum, local minimum term. Okay, so this implies f(0,0), okay, is not a local extreme value. Okay, it's not a local extreme value because in its neighborhood, somewhere is negative, somewhere is positive. No matter how it is. Okay, so you have if the second derivative is inconclusive for that point, but you still can find out whether the function has a local maximum and local minimum based on this. Based on the sign of the function. Okay. Now I remember someone took the quiz. Just say because the limit is infinity, that's why the limit doesn't exist. That I took 2 points off. You have to show the limit doesn't exist. You have to say in all the directions the limit is going to be infinite. Some directions not. Okay. As long as you can say along one direction the limit is going to be infinite, that's enough. That implies the limit doesn't exist. Okay, so this is the logic. Okay, for example, I remember the problem is x, y, right? X to the fourth plus y is 4. How do you prove the limit doesn't exist as x, y approaches the origin? Okay, some students say, hey, the limit is going to be infinity, but that's not true. When x equals 0 along the x-axis, the limit is going to be 0, not infinity. Okay, if you just enter one sentence along some line, the limit is infinity, then you get 4 credits. Okay, so that's why when you look at the quiz score, you get 13 points instead of 15 because your proof is not complete. And similar to the functions, when in one variable, we can also talk about absolute value, absolute maximum value, absolute minimum value. Okay, the theorem says that if the function is continuous, then on a closed domain, the domain must be a closed, a bounded domain. Okay, so here's the theorem, just like a closed interval. Okay, let f be a continuous function on a closed bounded domain. Okay, so that means including the boundary. They in R2. Okay, then the function, then f attains an absolute maximum value and an absolute minimum value. Okay, f with now x and y1 and absolute minimum value at another point. Okay, this is in D. Okay, the reason is the graph is not broken. So you can always find the highest point somewhere. This is a closed bounded domain. Okay, so you have a piece, not a graph, not broken. So you can always find the highest point, and that gives absolute maximum value. The lowest point could be the boundary around that, So this could be the lowest point on that graph. So it's possible the function attains an absolute minimum value at the boundary. So it's not easy. It's not easy to determine the absolute maximum value, find the absolute maximum and absolute minimum value. Okay, we can try. Okay, let's have still have some time. We can try to see if we can find the absolute maximum value. Okay, so this is a f x y. This is problem number 32. So it's going to be x plus y minus x times y. Okay, D is the closed triangular region. Okay, with vertices 2, 0, 0, 2, and 4 and 0. Okay, so here's the region. This is two-dimensional, right? With the vertices 2 and 0, 0 and 2, 0, 4 and 0, somewhere here like that. Oh. So the function defined on this triangle region was boundary, okay, including the boundary. So that's why it's closed boundary. We want to find out the absolute maximum value of the function and absolute minimum. So it must have absolute maximum value. It must have absolute minimum value. Maybe it attains the absolute maximum value on the boundary. Okay. So first thing we have to do is try to find any possible critical points inside the triangle. Okay. So let's find the partial derivative. Okay. So this is going to be it's 1 minus y. Okay. Fy is going to be 1 minus x. If you set this to be 0, so you get x equals 1, y equals 1. So you only get one critical point. Now, I'm not sure this is a point inside this triangle region. Okay, if I change it to, yes, I'm going to check that. Okay, so this is a line x plus y equals 2. Okay, right? This is a line x plus y equals 2. Okay, this is a line will be, let's find the equation, right? Here's a 4, here's 2. So this line slope is negative, so it's going to be x plus 2y equals 4, I think, right? Okay. when y is 0, x is 4. When x is 0, y is going to be 2. Okay. So this is a 2 lines. Okay. Now, so this is a point. The critical point is on the boundary, so it's useless because, okay, it's not inside the domain. It's not the inside domain, so there is no critical point. There is no critical point inside the domain. Okay, so in order to find the absolute maximum value, that means the absolute maximum value attains the function attains absolute maximum value on the boundary. Okay, so the function, let's find the absolute maximum value. Okay, So f attains an absolute maximum value on the boundary. So we have to find out, yeah, maximum value on the boundary. Now we are in trouble, right? How do you describe the boundary? The boundary consists of three pieces. Okay, so the boundary consists of three pieces. The first one, x plus y equals 2. So the meaning that y equals negative x plus 2. So x is between 0 and 2, okay? So now the function restricted to this line is going to be the first value is still x, second value is negative x plus 2, okay? So, so our function here is it's a problem number 32. So it's going to be x, y is going to be negative x plus 2, and the time minus x, negative x plus 2. So let's simplify this. X plus x, that's 2. You multiply this out, you get x squared minus 2x. Okay. This is a quadratic function. So you get x squared minus 2x plus 2. And what is the maximum value? What is the maximum value of the function for x between 0 and 2? Well, this is another problem, right? Yeah. So if you look at the graph of this function, this is going to be 1, here's 2, okay? When x equals 1, this parabola opens upward. So it's going to be x plus 1 squared and plus 1. So this is a parabola, looks like that. So the function has two, minimum value, maximum value, okay? The maximum value of the function is going to be at the end, the value of the function at the end point. So when x equals 0, which is 2, the minimum value of the function is going to be 1, okay? For the function for this function. All right, we solve this problem along this line. So we get to the, you see, what we got here is the value of the function along this line, okay? Along this line, the smallest value is a minimum value, maximum value. We have to look at this other line. The other line is x plus 2y equals 4, right? So this time for the simplicity, I'm going to let x to be 4 minus 2y. It's okay? Y is between 0 and 2. Okay. So fxy is going to be f4 minus 2, right? So here's x plus y. X plus y. X is 4 minus 2y, and plus y minus x times y. So it's 4 minus 2y and y. Let's multiply this out, okay? So it's going to be 4 minus y minus 4y plus 2y squared. So that's 2y squared minus 5y plus 4. Wow. So this is more complicated. All right, so we want to find out the maximum value or minimum value of this function. Right? It's not easy, right? Yeah. It's a parabola. If it's a graph, if you draw the graph, okay. So what is the maximum value? What is the minimum value? Now, the critical point. Again, you have to apply the theorem in for function in one variable, right? So you can, let's call it h. Right? We want to find absolute maximum value, absolute minimum value of this function. So h prime y equals 4y minus 5 equals 0, y equals 5 over 4. Okay, so this is the graph, and here's 0, here's 2, this is a point. The graph somewhere, let's see, what is the minimum value of the function? It's going to be 2 5 over 4 square and minus 5 over 4 plus 4. Okay, so so it's going to be 8. Okay, let me check. It's negative. I think it's going to be just like that. Okay. Yes. Then combine them. Okay, 32 minus 25. 7. Okay, anyway, it's positive. Okay, 25 plus plus 7, 32. Okay, so this is a positive. So parabola opens upward like that. Okay, I think the other side is higher than this side because it's close to 2. So clearly the maximum value is at the origin. The minimum value is a 7 over 8. Okay, so the maximum value is going to be f, is going to be h at the origin, which is 4. The minimum value is going to be 7 over 8. Okay. Yeah, this is a problem complicated. Yeah. So now the third one is along the y is 0, x is between 2 and 4. Okay, y is 0, x and x is between 2 and 4. It's easy. So x plus 0 minus 0. So it's just x. Okay, so for this function, the maximum value is going to be 4, minimum value is going to be 2. Okay, now the function along the three sides of the boundary, okay, you can have, you will see that 4 and 4, right? 4 and 4 should be the largest possible value. And the first one here is not 4, right? And the smallest value probably is going to be 7 over 8. So the function, you conclude that the absolute maximum value of the function f is going to be 4. The absolute minimum value of the function is going to be 7 over 8. 7 over 8 is the smallest one, that's the smallest value. So two-dimensional case is much more complicated than the one-dimensional case. If one-dimensional case, you just how to find the absolute maximum value, right? You find the critical points, critical value sometimes called, yeah. Then you look at the value of the function at the critical point and at the end points. You only have 2 end points. So you have basically you have you just compare those values. But for function in 2 variables, the boundary of the domain is a curve. And sometimes consists of 3 pieces. Sometimes it's just circle. So like in this case, I pick up a wrong problem, maybe I have 3 pieces, but this is the most complicated problem, right? Now you have to restrict the function to each side, and then to find out, determine the absolute maximum value, absolute minimum value, okay? So let's go back to this picture again. See, this is a picture. You see, you have to look at the value function along these 3 sides. You have to parameterize the 3 sides, okay? And then what is the maximum value of the function along this side of the triangle? What is the minimum value of the function along this side of the triangle? You have to figure out the number two numbers on each side. Then you compare all those numbers. Okay. If the function continues, then definitely it has absolute maximum value. Okay. I stop here and I'm going to post the lecture notes later. Okay. Bye.